We're going to continue the process from last class. And what happens is if we continue to cycle through the transition matrix, eventually our probabilities reach a consistent value. So our state matrix stops changing. It will eventually get to the point where if we run it enough times, every time you try to run the transition matrix again, you're no longer changing your overall values. So that is called the stationary matrix, which is the long-term behavior or probabilities of a specific scenario. That is what we are going to look at, find today. This was one of the examples that we did towards the end of class last time, and it was the housing trends. I want to say it was in Washington, D.C. We started with 0.419. I want to say it was homeowners, and then 0.581 was the renters, if I'm not mistaken. And then we had our transition matrix. So this one says, find S10, find S30, find S50 to see if we can determine what the steady state matrix is or the long-term behavior. So let me get my matrix calculator up here. I will enter my initial state matrix is 0.419, 0.581, and my transition matrix 0.847, 0.153, 0.17, oops, oh, 53, 0.174, and 0.826. So they want us to find S10, S30, and S50. So we're going to take A times our transition matrix 10 times. So 10 cycles through. 30 cycles, I'm going to change the power to 30. And 50, I'm going to change the power to 50. So you can see here, these values aren't much different from each other. We go from 0.5299 to 0.5321 to 0.5321. So that does not change any longer. And this one goes 0.4700 to 0.46789 to 0.46789. So you can see between state 30 and state 50, there really isn't much change happening at all, if any. If I round this, we're getting to the point where 53.2% are going to be homeowners and 46.7% are going to be 46.8% are going to be our renters. So I'll write these on here. I'm just going to round to, I'll go to 3 decimal places. Five, 3, 0, 5, 3, 2, 5, 3, 2. And sometimes I make a mistake and put a comma in there. There does not need to be a comma between the two values. Four, 7, 0, 4, 6, 8, 4, 6, 8. Oops. So because there is no change between these last two here, this is the long-term behavior, where 53.2% will be homeowners and 46.8% renters. That is what we are going to work with today, determining what that steady state or long-term behavior result is. properties of our steady state matrix are, if you take the state that you're in and you multiply it by the transition matrix, you get the same result. So S is the steady state matrix. P here is the transition. So if you take your steady state and you multiply by the transition and nothing changes, you have made the steady state matrix. The values in the steady state matrix must sum to 1. And no matter what we start with, eventually this will happen. No matter the situation, we will eventually reach a steady state. For this first one, I am going to show you algebraically the process that happens. And then I will show you how we can just use matrix operations together. Our first example says a Markov process has 2 states, A and B. So as I read this, I am going to put them into my transition matrix. The probability of going from state A to state B in one trial is 0.35. That means the remaining 65 will stay in A. The probability going from B to A in one trial is 0.25, meaning that 0.75 will stay in B. Find the stationary matrix that describes the long-run behavior of this process. So we are not given our initial state. So right now, I have some unknown values for A and B. But we know that if we multiply those initial values by my transition matrix, I should get those exact same values back out. What we are going to do is follow the process of matrix multiplication. If I take this row times this column, that's going to give me my first equation. So 0.65A plus 0.25B has to give me my first answer of A. Continuing with the matrix multiplication, I take my row matrix times my column here, and it's going to equal B over here. So let's see, 0.35A plus 0.75B equals B. What I'm going to do is I'm going to move the A and B that are on the right-hand side over to the left-hand side. So I am going to subtract A in this first equation over, and I'm going to subtract B in the second equation over. That is going to give me negative 0.35A plus 0.25B equals 0. Now, if I do the same with the second one, positive 0.35A, if I move the B over, minus 0.25B equals 0. Now, I have a slight problem here. If I were to work with these two equations, they cancel each other out, right? So I need to use the other fact from back here, which is this second one here. The values in the steady state matrix must sum to 1. So in essence, all I need to do is take one of these equations. I'm going to bring this one over here, 0.35A minus 0.25B equals 0. Only need one. And then we know our original A and B values must sum to 1. And now you have a choice of if you want to do elimination or substitution, however you want to solve this. I like elimination, So if I multiply the top equation by 4, that'll give me 1.4a minus 1b equals 0. And then a plus b equals 1. So that my b's can now cancel out if I vertically add. Vertically adding my a's, 2.4a, b's cancel out equals 1. So then if I just divide by 2.4, a is going to give me about, I will round as best as I can here, 0.41. It's going to be 66666 repeating, so I'll go 4167. And then we know b has to be 1 minus that value. So that'll be 0.5833. What we found is we are saying that A will remain 0.4167, B will remain 0.5833 in the long run. And the way I would check would be if I multiply this by my transition and the values stay, I've done it correctly. So if we wanted to do that quickly. Matrix, row matrix, 0.4167, 0.5833. And our 2 by 2 was 0.65, 0.35, 0.25, 0.7. Oh my goodness. There we go. So if I multiply those together, is it still 0.4167 rounded and 0.5833 rounded? Yes, it is still the same answer. Now, I understand that's a lot of algebra involved, and we have access to technology. So are we going to do all of this by hand in the end? No. We're going to look at another one here. And this one has 3 states. So clearly, I'm not going to do this one algebraically. This would be a 3-part system. They're not fun to solve by hand. A Markov chain has 3 states, A, B, and C. So I'm going to, as I read this again, create my transition matrix for A, B, and C. The probability going from A to B in one trial is 0.75. The probability from going from B to A in one trial is 0.2. B to A is 0.2. So that one's in the second row. The probability of going from A to C is 0.2. Back to the top row. A to C, 0.2. So I've accounted for 0.95, leaving 0.05 left for A to A. Keep reading. The probability of going from C to B, so third row, C to B, second slot, 0.15. Probability of going B to C is 0.15. Second row, last spot, 0.15. Counting up that row, I've counted for 0.35. That's going to leave 0.65 for B to B. And C to A, first one in the last row, 0.40. Total of that so far is 0.55, leaves 0.45 to remain in C. So here's what we are going to do. We are going to take our transition matrix C. And all we need to do is check it to high powers. We saw in our first example that 10 wasn't high enough to get to our steady state matrix for this one, but 30 and 50 were the same result to get me to my steady state matrix. So what I need to do is I just need to start trying. 10 is probably not going to be high enough. Generally, I suggest start with 30. And then you can always double check another one above that to make sure everything is good. When I put in this matrix 3 by 3, 0.05, 0.75, 0.2, 0.2, 0.65, 0.15, 0.40, 0.15, 0.45. I'm going to take this matrix and I'm going to raise it to, like I said, the 30th power. Here's how I know that I've gone high enough. Every value in the first column is identical. Every value in the second column is identical. And every value in the third column is identical. When you have, I'm going to roughly round this. 0.2138, 0.2138, 0.2138. 0.5566, 0.5566, 0.2296. So what happens if I have my initial values, no matter what they are, first row times first column, they're all being multiplied by the same value. So I'm going to get an answer. If I cycle through this transition matrix again, that's not changing. The transition matrix has now reached a point where it's not changing anymore. So no matter what I multiply into it, the result is going to stay the same. So my steady state, or my S, is just one row, 0.2138, 0.5566, and 0.2296. So if you cycle through your transition matrix enough so that every row is identical, one single row has created the steady state matrix. So A, B, C, end results. Next one. 2 popular brands of macaroni and cheese, Smack-A-Lot and Good Eats, are sold at the grocery store. The buying habits of customers are followed for several weeks during an advertising campaign. As I read this, I'm going to put my matrix together. So Smack-A-Lot and Good Eats. Smack-A-Lot, Good Eats. It is found that 10% of those using Smack-A-Lot will switch to Good Eats. So 10% from S to G means 90 are going to stay. And 30% of those who started with Good Eats are going to switch to Smack-A-Lot. So G to S, 0.30, leaves 70% is going to stay in Good Eats. If the trends hold up, what percentage of customers will use Smack-A-Lot and what percentage of customers will use Good Eats in the long run? As long as we can create our transition matrix, we can then take it to a power. So let's see, 0.90, 0.10, 0.30, 0.70. Again, I always like to default just to 30 because I feel like that's generally high enough. And we have gotten our steady state of 0.75, 0.25. So in the long run, 75% will have Smack-A-Lot and 25% will have Good Eats. Now, why does this matter? Well, if you are Smack-A-Lot, you're going to be decently happy with these outcomes, right? If you're following habits and you see that in the end, you have a higher customer base, that's good for you. You're going to keep doing what you're doing. It works. However, if you were Good Eats and you were tracking this, you would say, there's a problem. We need to do something about this. Do we need to change our recipe? Are people not liking our recipe? Do we need to do a consumer research survey and figure out why people don't like our product? Do we need better advertising? Do we need better sales? What do we need to do to change that result if we were that other company? That makes sense? We have one more. And then that is it for today. The buying patterns of customers who buy 2 brands of running shoes, Flying Feet and Great Grips, are noted each year. It is found that, as I read this again, I will make my transition matrix. So Flying Feet, Good Grips. 90% who buy Flying Feet one year will buy Great Grips the next year. Ooh, that doesn't look so good. 90% left this to go to the other company. Only 10% stayed loyal. So that should be a giveaway right away that your Flying Feet is going to have overall a lower percentage than Good Grips, especially when I read this next part here. 10% will buy Flying Feet again the next year. We got that part. Also, it's found that 20% of the customers who buy Great Grips will buy Flying Feet the next year. So only 20% left Good Grips. 80% remained. So again, you're seeing higher percentages with Good Grips. So we would expect in the end, their percentage to be higher overall. All right, make our matrix. 0.10, 0.90, 0.20, 0.80, and raise it to the 30th power. So I've got about 0.182 and 818. 0.182, 818. So in the long run, 18.2% Flying Feet, 81.8% go to Good Grips. So clearly Good Grips looks to have, whether it's better quality, better durability, they've got a better product than Flying Feet. That is all I have for this. So you'll work on your homework for chapter 9. Next week, we will start on Tuesday. We'll do 3.1. We're going to move backwards to chapter 3. We are going into our finance section. So I always like to put finance at the end just because sometimes it's a little more complex with different formulas and stuff. And with it rather than kind of start the semester with it. But I always give you Desmos. We've got some Desmos tools. We've got loan amortization calculators. I'm going to show you some additional tools to help you as we're working through those. And then Thursday, you'll be able to take your chapter 8 and chapter 9 test. So work on your homework. If you want, look over the review for the exam. So like if on Tuesday, you're looking over like, hey, I don't remember how to do this type of question. Can you help me? Can we go over it? We can do that on Tuesday. Otherwise, have a good weekend.